Good.
Yep.
We're back after the break, and it's running. It is a little after 5:45 on our last seminar day. As I mentioned before the break, I wanted to touch on some concepts that are consistent, ideas across modeling in different types of modeling, the model these things are all interrelated in the working of a model. And there's much more context to understand about how models, what can be represented by a model and what cannot. And it's important to understand that fundamentally, most everything we deal with is far more complicated than can ever be fully characterized by any finite systematic description. I mean, there's not, I mean, the complexity of the natural world is far beyond what we can ever hope to achieve. So a good model is any model that is a simple, finite, it's not a large thing. It's a simple thing that we can understand and do in a week or a month of time, and that does a good job of describing some aspect of the natural world in a extremely simplistic way. And that's all that these models do, is they take something that's too complicated for us to understand real well, and it applies a simple structure of linear combination of factors in a linear regression model. And those factors are the things that we use to explain some response variable, and then the part that we cannot explain is what we call the random error. That's the error term in the model, this thing at the end, the last term. And it's very often the case that there are systematic things occurring in that error term, but trying to explain those and characterize them and trying to obtain data to measure them gets into levels of complexity that are you easily get into into countably or even uncountable infinite sizes of data and computational problems to try and express natural things that are anyway. So often, very often, what a model does is it gives a very simple, a horribly crude, simple description of a very narrow aspect of the real world, and hopefully it does a good job of describing a very, very narrow, simple, little, tiny portion of the real world. But that context, that narrow little slice, is very critical to the models. The context in the case of QSAR is, you know, some group of molecules that is being studied, some response that is studied. If this has to make some sort of natural sense to a chemist in a chemistry context, and it has to be sufficiently limited that it can be, that the relationship between the response or the endpoint or the response, the thing, the Y factor that you wish to model, the relationship between that and the X factors which you have data about or create from structural information. This has to be it can only, it is a very simplistic view of a molecule, and, you know, using these X factors to explain some Y factor, some molecular descriptors to explain some endpoint. And because it is so simple and crude, it must be within a very narrow context that this can possibly apply, and that gets into the domain of applicability, where if you consider, sorry, I went too fast, where essentially the model in application, after developing the model is then applied or interpreted across a domain of, in this case, chemical molecules, which fall within the appropriate context, the chemistry context. And the key thing is that this domain where the model can apply must be integrally connected, and the statistics theory comes in, where statistics works when you have representative data. Data must okay. The domain of application is limited to the set which is statistically represented in the data. This is the training data, or the development of the model data. So statistics theory applies through random but representative random sampling. And if sampling is too sparse, it does not sufficiently represent the aspects of complexity in the system, or if there are holes or areas of some general domain or class which are absent, there are missing areas, then that without data to represent those areas, it is inappropriate to try and apply a model across the domain that includes those areas with holes, with missing information. And this is sometimes difficult work in QSAR. It's it's non-trivial to develop this domain of application, because these molecular descriptors that are used are often not natural kind of quantities. They might be topological indexes, connectivity of a graph theory thing, the number of vertices connecting of separation might be various. So not necessarily a clear physical sort of context that you can understand what exactly the full spectrum of values might be. So a simple example, looking at like height and weight of people, right? Height, weight, we wish to have the weight of people predicting the height of people, and we ignore in looking at this weight as a function of height as a function of weight. We can do this study, and we can do sampling of people of some defined population, and we can sample, and there are always problems in sampling the real world. Your samples are never what you want it to be. And we develop our model using the data that we collect and measure for the people in the sample, but we find out that there was a problem with women, and they were not measured. So there's the sampling went through and did all the everything, and now we have a model which is based on data which looked at only half the population and ignored some important, gender differences. And so you develop, this is the kind of thing that you see errors made often in literature that just, make me want to cry when I see these things, that people do horribly stupid things. Make horribly stupid mistakes, like ignoring classes classes within some domain, and then applying the model to that. And in this dumb example, you end up, if you're not careful, you try and model the height of women the same as you model the height of men, and it doesn't work. So that would be something where there would be a hole in that domain, that space of data was missing a large category. This is the same, this is very similar in conceptually to issues of interpolation and extrapolation. So extrapolation is usually to be avoided because that goes beyond the end of the data to extrapolate in some area where there is nothing, is no information. If this is the range of some data. And so you study a certain range and then extrapolate the relationship into an area that you have no information about. Or interpolating would be if you have some information and along here and you establish some relationship, but you are missing some chunks. And with interpolating, using the information on either side and hoping for consistency across the missing chunk. Okay. There's the domain, the data, importance of understanding what the data is exactly. That's where the most mistakes, I believe, in my experience with the real world, is in the mistakes of wasted time, where people spend days and months and huge amounts of money with employees doing analysis where there's something that's wrong that someone discovers later in the process after a huge amount of time and money has been spent, when it is discovered that the nature of the data is just not exactly the way it is being interpreted in the analysis, which eventually leads to some errors in the interpretation or application of the modeling, and the whole thing, and a year of work is trash. Not so much errors that make it through to publications, although there are situations of, things like that have come through and people die. But so data, applicability of domain, and training. Everything, all of these different models have some aspect of training. Something that's conceptually similar to training. With regression, with linear regression, training consists of computing some matrices, algebra. That's what the development of the model, training or develop the model to figure out what are the relationships, how does it work, what are the, in linear regression, what are the beta parameters, what are their standard error, are they statistically different from zero? These are the things that are the mechanical aspects that, and they are derived from some direct computation. And in, you know, determining the slope of the line, right? It's not a difficult thing to do. Delta X, delta Y, whatever. It works a little more complicated with regression, but it's the same idea. That's a very simple sort of training idea. Another more abstract method of modeling that's strangely seems a little bit abstract to us, but it's how our brain, it's the idea of modeling in the way neurons work in a brain, and that's with neural networks, where the model is, there's different styles, different groups of these things, but basically these things work by setting up some structural aspects that relate to, you know, neurons with connectivity and functions between the neurons of signaling, the signal input-output functions of neurons. And then there's weighting factors or parameters in these functions that say whether or not the signal is passed on and what is the strength of the signal. It's designed on how the biology side thinks the brain connections, the neural connections work vaguely, in an abstract sense, and the training is essentially a matter of having a bunch of, right, there's a bunch of input data like X's. X's that go into this box, and there's some information that comes out, which is the Y value or values or locations, or this can be, these are very free form kind of models. So you have just some input and some output, and in between you have this pile of computer simulated neuron connections, and you start out with the training by having an additional input, which is the result, the known training example, which tells the thing, for this set of input data, what is the result supposed to be? And then the computational, the training computation algorithm just starts, there's different styles of feed forward, and well, there's a lot of different algorithms to implementing the training, but basically the training is adjusting parameters having to do with the signal transmission through the neurons and the functional form of the output from each point, and they modify it in different ways so that it converges to some solution of parameters on these things. Each one has a bunch of parameters, and it tries to adjust those parameters so that the training examples come out the way they're supposed to be. And that's a very, very free form, it's a very, very free form modeling, but it's very kind of black box. It's difficult to, I did a lot of work and research stuff with neural networking and computational theory stuff, and it's very interesting, but neural networks are not conducive to understanding why it gives the results it does. Many neural networks are set up as a complex set of linear functions, or something that transforms to a linear function. So they are fundamentally they are linear models, but they are with multiple stages of linear transforms being applied. It's very difficult to sort out. You get some result. There's some x values that go into this thing that are the input, along with an actual y value. And then there's some output, which is some predicted y value. When I say value, it could mean many different things. It could be a category, it could be a place, an area, a level of a signal or a frequency. Or many, it could be a vector of quantities, or a space of functions. Okay. So you have the actual output, you have the output of the model, and you have the actual true result, and the reason for the model prediction matching the reality or not matching with reality is very difficult to figure out from the huge complex mess of functions and connections that are going on inside the neural networking. But they are very, very flexible things. You can just throw training examples at them, and it can learn to classify or scale or do whatever as the way you show it to. But you can have problems of over how do you say that? Too smart, or you can end up with a neural network that's a little bit too complicated, a little bit too sophisticated, and you give it 10,000 training examples, and it is supposed to find from this some, set up a simple set of rules which classify or measure the level of some result. But if the thing is too sophisticated, you might end up with the neural network simply memorizing the 10,000 examples that you gave it. And I mean, functionally, it's difficult to figure out what it's doing, but fundamentally it might just memorize what the examples are, and when a new example is given, the model is unable to correctly classify it because it can only correctly classify things that it has seen. That's learning by rote or memorization, and that's not what you want from a model which is supposed to generalize and simplify things rather than just regurgitating the data that you show by example. There was a great, very early neural network, one of the first functional, serious neural networking projects was the United States Army's DARPA defense, the advanced high-tech research area of the United States military. And so there's, they had pictures of, this is to try and teach a neural network to digitize, to see a digital representation of a photo or of a video sensory that, you know, is a forested area, a camera in the woods, and whatever that looks like. Those are trees, right? A camera in the woods. So the woods look like this as compared to the same picture, but it's the military, so what do they want to see? They want to know whether there's a tank in the woods, right? So just a simple detection of presence of a piece of large equipment in the woods, and they took thousands and thousands of training example pictures. Some examples were pictures of the woods, that's trees, and some were examples of pictures with trees and military vehicles in the woods. And then the idea is to train this neural network. This is maybe 1965, I don't know, long time ago. Tried to train a neural network to flag these as a 1 and these as a 0. And it got very, very good at determining which is woods and which is military vehicle in the woods. They later learned that it was useless because the people that took the pictures had to put the military vehicle in the woods to take the picture. And they tended to do that on days when it was nicer weather, when the sun is shining. And this is between North and South Korea, and so it rains a lot. And so generally you have pictures of the woods with rain and pictures of military vehicles when it is sunny. And that's what the thing learned, is it learned to tell the difference between rain and sun rather than woods and military vehicles. But they couldn't tell that until long after it was done. And it was a matter of the fault of the training data. With linear regression, with multiple least squares regression, you may have potentially much more data, X factors, different values, explanatory factors. You can have potentially, you can have as many as you want with all kinds of different information. And at some point, if you approach the number, as the number of factors, number of factors increases, relative to sample size, as the number of factors increases, relative to the sample size and number of factors P, sample size N, you end up, you start approaching, it approaches well, a degenerate what you in practice it approaches having no error degrees of freedom. Equivalently, it has as many explanatory factors as there are data, and so it is essentially the same thing as just memorizing, like with the neural network. It is analogous to just memorizing the data or setting up a unique parameter for each unique value. It doesn't generalize relationships, which is what you want. This, oh, Christ. The matrix is not invertible in that case. And the matrix, the good software will let you know as you approach that point, and the statistics become unreliable. There's lots of problems there. It's just, it's a situation where the neural network, you don't know what it's doing. With the linear regression, you do know what it's doing. It's doing something simpler, but you can see flag the problems and identify, oh, here's my example. I was wondering that. If we have y values of 2, 3, 5, and 7, and we have explanatory factors x1, x2, x3 of whatever, 1, 1, 1, 1, 1, 0, just two level 0, 1, 1, right? You can set up just a trivial example like this, where you have unique data for each row, and you have a factor that is across the three factors. The three factors are sufficient to identify uniquely the four different values in the data set. And so even if nothing else, you can always do this even with simple regression, to just make your function y equals beta naught plus some polynomial of degree p for p factors, or plus 1 or minus 1, I'm not sure. For p factors where p is about equal, almost as big as n. This is just, any regression model can be set up. If you have too many factors, you can just set up and just essentially plot a transform of a polynomial through the data, and you have, it's like taking a few data points and trying to, you're trying to get a straight line through the data, but if you have if you have more parameters in the model, it can just go through this and plot this nice polynomial function through the data that hits every data point exactly. The model looks great because it hits everything. That's wrong. It hits everything exactly, but it's useless because it doesn't characterize any generalization. This is not the relationship between these two values. It's this general straight line. So that's my warning or discussion of the problems associated with training models or developing models, that there are some models that you know how they work, like regression, which is one of the reasons why people use it, and that there's these problems that can come about in training which are essentially equivalent to overfitting or memorizing the data in some sort of equivalency to that, and or to memorize or to learn the wrong pattern. You want it to pick up on the pattern of associated with something, but due to a problem in the data, the domain of the data isn't structured correctly, and it picks up on something completely different, and you may or may not be aware of it. And those concepts, that data that goes in to a model, the domain, the statistical, the data and the statistics, the sample and the model application, those domain ideas, and the training or development of the model, they're all together, and I just wanted to touch on those briefly. And another thing, what was it? With training, I should say, just because it's quick and easy to say. Often, very often, not with regression, but with other things, very often, models are trained using, a 90% set of the data to determine the model, to train, and 10% of the data is withheld and used to evaluate the accuracy of the trained model on data that the model has never seen before. So that's a fresh look at it. That's an important concept that comes up and is often mentioned in QSAR papers in particular. They seem to do a good job of often discussing that aspect of the withheld data. Okay. All right. So there is a little more time. So I can go on. What? It's very disappointing because it's just at the edge. We got almost far enough to do something interesting in this seminar, but not quite. Let's see. I can just start throwing out methods and well, no, I'll generally in statistical modeling. There's univariate and multivariate. Models or techniques. And the characteristic difference, although it's not always crystal clear, but a univariate model has as a response variable that you are trying to predict, the y variable is a scalar. is a scalar for an independent unit. And with multivariate modeling, the response variable y for the independent unit is a vector or a set of values, it is more than one data quantity. And with, it's a vector value quantity with in the normal distribution case, the correlation or not divided by the standard deviation, the products, covariance, Christ. The covariance is a vector with a covariance and so a little more technically, that means that the values, there are more than one value, one aspect of the response. It's not just a single measure, but multiple measures. And there's covariance or correlation within the independent statistical unit. There's a correlation with it for those quantities, which basically, I mean, what that means to me is that the covariance matrix has off-diagonal components that are non-zero. If you like covariance matrices. Anyway, multivariate modeling is much more complicated and is a wonderful, wonderful thing that fails in its end use in the real world due to it being just a little bit too messy and difficult to be a robust, reliable tool. There are just so many cases where it's appropriate to use a nice multivariate model, and that is done to understand it, but for the final result that means something, there is a reduction. You reduce the vector quantity to a single y factor for any final meaningful analysis, because you're just not, I mean, people generally are not quite as comfortable with the complexity of the multivariate. So the battery is gonna die, it says. It should be, it's plugged in.
Maybe with a little less intensity of light.
Okay. That's fine.
Because
I don't know why it's not. It's not warm.
No, es que el problema es que cuando tienes mucha luz, when you have too much light,
Yeah, but why is it?
Battery.
Is it saying it's charging?
It is. Yeah, it is charging.
Okay, now maybe it just wasn't quite.
It's because there's too much light, so it takes more
Okay.
energy than.
Yeah, no, I see. It has to backlight the LEDs on the screen more. Okay. Multivariate models, well, I'll stop. I won't get into that. ANN. Artificial neural network. Basically, this is just writing the program for the mathematical calculations which simulate the connections like neurons and signal strengths and cutoff functions with probabilities. When you do more advanced neural computing, you have to look at also incorporate probabilities in the information entropy on the signal theory stuff. It can get messy, but in practical implementation, there's lots now. There's lots of software where this is already done for you, and you just need to plug in some data and try different training methodologies. So there's different. So artificial neural networks, basically you're looking at differences in or choices in training method or training algorithm, training approach. Some training approaches are much more computational, some are much less computational, but require more examples, and sometimes the adjusting, essentially the converging on the solution can take longer in different, there's supervised and unsupervised, where in supervised training, you sort of preload it, pre-train it, because you know what it's supposed to do. So training approaches, and the other thing is just generally the structure of the neural network. There's some structures, it's just a bunch of functions. That's all it is. It's not neurons, it's just a bunch of mathematical functions implemented in a computer program. But you can imagine that there's, these neurons that are the inputs, and then there's another layer, there's multiple layers with degrees of connectivity so these neurons have inputs from these neurons, which get the raw X value inputs. And there's functions. This thing takes a function of that and passes it on here. And this thing is a function of these inputs and some parameters of the function. They're all f of a vector of data and a vector of parameters. And depending on the parameters, and the function is defined by the parameters, and the data is what comes in from up the river, upstream, and it flows down into an output. A popular generalization of regression. How do I say that? K nearest neighbors is one that I kind of like because I do a lot of work with these nearest neighbor searching approaches with LiDAR scan data to identify features, like find the individual trees and features in forests or scenes. Anyway, but these are computationally intensive, high-dimensional searching kind of algorithms. You can think of a two-dimensional situation. Oh boy. Oh, sorry. I wanted to, well, okay, this is a type of metric or geometry sense of closeness. And it's more complicated than you think to find everything that is close according to some defined measure of distance. But the nearest neighbors, or the nearest neighbors neighborhood kind of approaches, are trying to identify a neighborhood around a known point. So here's a known value, and identify a neighborhood which has the proper, this neighborhood is the similarity neighborhood. It's the things that are similar, that are defined in the model, you set up to be similar to this point, to a certain degree of similarity, or a certain number of similar objects. That's where K is the number of, K is number of nearest neighbors to some point. So 1, 2, 3, 4, 5, whatever. And the geometrical, having some defined distance function or metric saying to measure what is close, and then to be able to derive with lots of various search or basis function tools to find a region in some space of variables which you associate with this specific, with a specific thing that you know what this is. You know what this is, and you try and find everything that's nearby. And you have something else over here, and you know what that is, and you try and find the neighborhood that goes along with that. It does not have to be geometrical, but there does have to be some sort of metric to use to set up neighbors. Very computationally intensive in searching, especially if there's high dimensionality. Logistic regression is worth mentioning. Oh, I should say that the nearest neighbor idea is a somewhat more general version of regression modeling, where regression, you have some point that you know where it is, you know what it is, X, and you are looking at the neighborhood of Y values that are around that X point. So it is analogous to, regression is a very simplified type idea, similar in to the nearest neighborhood approaches. Okay, logistic regression. Logistic regression is a generalized regression, and there's also regression for, so logistic regression means binary or class, because you can do multinomial or classification levels, treatment level. Logistic regression is fundamentally identical to binary logistic regression repeated several times. It's provably equivalent to just, so you can, this is when you wish to predict a response Y, which is a 0 or a 1. That might be a no or a yes, or multiple categories, where you would call it multinomial logistic regression. Like I said, it's just a iterative of logistic, where you could be predicting a classification group like A or B or C. This is the kind of thing you often do with neural networks. Is the response, it's a categorical response. You wish to classify things, and neural networks classify things very, very well. Logistic regression also does a great job of classifying things using some set of linear functions. It is a linear model, general linear models. Logistic regression, Poisson, is when the response is a count. And it's another set up very much the same as a multiple regression model. There are a lot of differences in the mathematics of applying some transforms, but it works very much like multiple regression, but with needing to tell the software that the response is binary or is a count data, like the number of bacteria that survive the pesticide is the count, often expressed, or the odds of an event, a probability, can be worked in with the binary, or a multinomial classification. There are more, anything in the exponential family, distributions, etc., with a transform, and you can do a whole lot of stuff with variations of regression. Clustering algorithms. Clustering is where there is some notion of a distance or a metric function that measures similarity or closeness, or in some kind of response variable measure, and that's similar to nearest neighborhoods, where you have some notion of being able to measure a consistent measure that's in a sense a geometry saying of similarity. Let's see, metric for similar data, for similar units. if you have two chemicals with a bunch of, or if you have a bunch of chemicals with a bunch of measurements on a bunch of characteristics or molecular descriptors, and those, and there is a, given the situation, there is some sense, some chemistry context sense of a measurement that tells you which things are more similar. And then you have what is essentially a big geometry. Here's the two-dimensional version of perhaps many, but often, usually many dimensions. X1, X2, and we have data scattered around this space, and there is some function which is not necessarily any kind of geometry thing, but is a consistent way of measuring, of inputting. It's a function of x1 and x2 for two different points, and it tells you, and it measures that these things are closer than these. Now that may not be, that's in a geometrical sense, that is a distance, but that might not be what the similarity measure might not have anything to do with the geometry. Might be a transform or include alternate, completely non-geometrical kind of things. It can be really any kind of function that satisfies a metric, and it may happen that the way it works is that it also incorporates the response, y, in such a way that you have groups that are all very close together. These are all these things are close, and these things are, I don't know, and then you have some things that are a little further away, and they're shaped like this, where this point and this point are as similar, are just as close as these two. Right? It doesn't have to be in the right shape, but then if you have this situation, there's the nearest neighbor approach of algorithmically searching around points that you know for other points that are similar to the things that you know about. Clustering is where you don't really know where to look. You need to search the space to find groups that bear similarity. This is often in two-dimensional data. You know, a chunk here and an area here and something over here, and you want to, if you have, in a two-dimensional picture, you can look at it and say, okay, I have a group here, and I have a group here, and I have a group here. You can look at the picture and identify it. If you have 100 dimensions, you can't look at the picture and identify it, or even 4 or 5. You very quickly, as the dimensionality, as the number of factors increases, right? The dimensionality increases very commonly in the range of 20 or so. Is not a lot of factors, but it's a lot of dimensions, and the number of corners and pockets that exist in a higher dimension, even a Euclidean space, it just increases exponentially. And so you get what was a simple thing in 2 dimensions that I can draw a picture of is far beyond our ability to visualize or see from pictures. And so there are algorithms that are called clustering algorithms that find that, generally speaking, what they do is they attempt to find groups which is an area which has similar things with some spacing to another cluster, and so it kind of breaks down the space. There are other similar tools of partitioning algorithms which, instead of identifying the cluster of similar things, a partitioning algorithm hopes to identify the lines that best separate kind of a gradient ideas. And very, very interesting, fun stuff that with, if you have plenty of computational power, they're very, very interesting. What's missing? When I look at QSAR modeling statistics, and I look at the algorithms and the methodologies, statistical modeling that is used, and it is quite advanced, recent, high computational, great stuff, but there's no sense in the modeling of frequency domain or time dependency or any kind of Fourier approaches, which I don't know if it applies or not, but it seemed rather outstanding in terms of missing from the context. And I think, what time is it? Yes. We will, so frequency, what's missing is generally frequency or time, longitudinal domain analysis, which probably could have some place, but doesn't show up. Let me wrap up, and we will end in just a minute or two. Please feel free to contact me, Damon, Bell, USFQ at gmail.com. You can write in Spanish if you like. We have, we had to cancel a class and we stopped short, and because of that, there's at least several hours there. I'm quite willing to answer questions or entertain discussions or arrange something, whatever. I'd be interested to know what people think, or any work that people might be interested in doing. I'd like to have involvement with that, would be great. Is there anything? Evaluation. I mentioned that briefly before, that we will do something along the line. along the lines of a email with a form, a test, or an exam to not so much evaluate the level of your understanding, but rather to that, you know, some presence, some awareness of the topics that were discussed and presence in listening to the seminar as as some sort of confirmation. I would not expect it to be challenging. Okay, we will wrap up. Thank you very much.